So chapter 7 and going forward really begin the point where we kind of combine our first, what I'd call quarter of the semester, where we talked about distribution shapes and means and standard deviations and z-scores, and the second quarter of our semester where we discussed probabilities especially. And using those two concepts in conjunction, we'll be looking at what we will call a probability density function. And so the idea here is it's a function or a graph, you can think of it as something that represents the different probabilities of a given variable over certain, we'll say, intervals for now. And so we'll see what these things mean as we get to some more actual concrete examples. But the idea, if it's a function that represents probability, we're going to really focus on area under the graph. You're going to see that be the key point of these graphs, these functions that we take a look at. And so, since the area under the graph, we're going to find out, does represent probability, then this is a fundamental rule. We must have that the area under the graph for the equation is equal to 1, because that area needs to equal probability, and so we've learned before that 1 or 100% is the entire probability or proportion of any kind of variable you're looking at. Now the height of the graph, it says, must be greater than or equal to 0. That even there really does follow our understanding of probabilities, because we've mentioned before that all probabilities are values between 0 and 1, whether they're in fractional or decimal form. So it makes sense that we would not have any function that went below our horizontal axis, because it wouldn't make sense to have anything with a negative probability. So again, we'll elaborate on these as we get into some examples here. So speaking of examples, I'm going to have you read through this paragraph here, and I'll give you just basically pause the video here and come back, and I'll summarize it. So we're looking at the idea that a parcel, a package, can be delivered, and we're going to stick with this window of 10 to 11, but we're saying it's equally likely. There's an equal opportunity that that package is delivered at any point, starting at 10 o'clock and going to 11 o'clock. So 1 hour, right? 60 minutes. So we break apart that 60-minute interval into what we could just consider 1-minute intervals, so 1 minute at a time, to say that if it's equally likely, or the probability of it occurring at any time is the same as any other, like them being early versus being very almost at the end of the time frame there, it's all equal. So we're saying every single interval of 1 minute would have the same chance of it arriving. So whether it's 10:15 and 10:16 or 10:40, 10:41. And so we're going to represent that scenario with this graph below. Let's see if I can keep this on the page there. So this function, now this is a uniform density function. Uniform because we saw that word back in chapter 3, or actually 2, with distributions. Uniform being the function or the graph having that kind of single height, right? Single frequency in a sense. And so we're saying from what we could call time of 0 minutes starting at 10 a.m. up to 60 minutes later at 11 a.m., the idea that the chance that it occurs at any 1 minute interval here is this 1/60th, right? There's 1 minute out of 60 minutes in the hour. And so this function creates this picture to describe the probability of when that package would be delivered. Now notice it's a rectangle. And using the basic formula of the area of a rectangle, area is length times width. Well, if you want to call this the length, it's a length of 60, going from 0 to 60, and a width of 1/60th. So notice the area under this, if you want to call it a curve or function or graph, that's the graph right there. Just a line, horizontal line from here to here. The area under that curve from 0 to 60 is exactly 1. That's 100% of the possibilities of when that package will get delivered. That's the idea of a probability density function. Now this is a pretty boring one because it's just this idea of an equally likely event. So as we look at the next page, we'll just take a look at one example, one situation here. What if we were asking the question of what's the probability that the package would arrive between 15 and 30 minutes after the hour? So basically 10:15 to 10:30, right? So again, here at the top of the page is what I mentioned before, that we understand that the area under the graph represents probability, and specifically with any interval that you look at underneath that graph. So the interval here that I've got shaded is running from an x value of 15 to an x value of 30, and we're saying that this shaded region under the graph, right, from here to here, creates that smaller rectangle. The area of that rectangle should represent the probability of the event occurring in this interval from 15 to 30. Well, we just said every minute has a 1/60th chance, so it would make sense that for 15 minutes it should be 15/60ths, right? Well, it does make sense because we've created a rectangle that is 15 long and 1/60th wide. So again, if you looked at the area of that rectangle, the length there we could call 15, and the width is still that same 1/60th, which would be the 15/60ths, which also reduces to 1/4, which 15 minutes is a fourth of an hour. So that's it. That's the idea of area corresponding to the probability. Okay? So we extend that to a different distribution, one that we've seen before. Now we give it a new name. We would recognize this shape as the bell-shaped curve from chapter 2. But this shape, this distribution is so common in nature, in various populations, that it's been given another name, the normal curve. Think of it as something you would normally see. But the normal curve is the name we will use from this point forward. It is still bell-shaped. You can still call it symmetric. But this shape, this bell-shaped curve, we will refer to more often than not as the normal curve going forward. And so, a couple important things about this. Some things we've learned and some things will be new to us. One small detail about the normal distribution here, the normal curve. And we've talked about this when we first saw the bell-shaped curve and really dove into it around the time of the empirical rule and stuff like that. This bell-shaped curve, which we'll see more of on the next page, has these points that we call inflection points. And the real idea behind them is just, you can think of that point as the point where the graph changes its curvature. And what we said when we learned about these before was if you look between the points, it's making what you could call an upside down U shape, right? From here to here, it certainly looks like it's curving like an upside down U would curve. But as soon as you hit these points and get beyond them, notice the curvature, it's now curving in the other direction. And although we only see half of it, we can imagine this would be more of like an actual, a right side up U shape. So you have this U-shaped curvature to either side of the inflection points and an upside down U-shaped curvature between them. It's really just a distinguishing characteristic that we note for graph purposes, and there'll be a couple questions regarding inflection points throughout the homework. But on the next page, we really dive into a lot of details, several of which we have discussed prior regarding the bell-shaped curve. So this will be a little bit of review and some new stuff as well. So properties for the normal curve, normal density curve. So it's symmetric about the mean being mu or x bar, depending on population or sample. But the mean is the center, right? Symmetric about it means whenever you draw the picture, even if I go to this one here, we've always known the mean is at the center, at the peak of that bell-shaped curve. So then we've got the second property here, because mean, median, and mode are all equal, or theoretically the same. The curve has a single peak and the highest point occurring at that mean. So again, same idea. This position is both the average, the middle, and the highest point of the distribution. We just mentioned number 3, the inflection points at mu plus, that should be a plus, mu plus and mu minus sigma. So that was on the previous page. I didn't actually highlight that information, but if you go back there, it is on that graph. To make that what we call the jump of a standard deviation, one jump to the right or one jump to the left puts you at the location of those inflection points. Here we have the very important idea of this being a probability density function, that the area under the curve is 1. The next one follows directly from the fact that it's symmetric about the mean. If it's symmetric, it means it looks the same to the left and to the right. It should have the equal area to the left or to the right. In other words, half. If the whole distribution has an area of 1 underneath it, then half should be to its left and 1/2 should be to its right. So that's, again, tying in the area with the idea of symmetry with the mean there. So now, number 6 here, kind of wordy. As x increases without bound, meaning as you go left and right forever, The graph approaches but never reaches the horizontal axis. So theoretically, with a true theoretical normal curve, you've got this curve going out and it gets really, really close to the horizontal axis or the x-axis here. And we've talked about this too. We've talked about the empirical rule. In fact, this whole graph here is nothing but a summary of that empirical rule we learned. And we even said how, even here, we're not going to say it touches or stops, but it just gets to the point where we don't draw it anymore because you can't draw it and have any meaningful distance between the graph and your horizontal axis. So that's what that's referring to. And 7 is specifically just referencing all of our known information from the empirical rule. Not only the 68, 95, 99.7 being between the 1, 2, and 3 standard deviations, but all the extra little, individual sections that we then know the probabilities or the percentages of because of that distribution. Now, going back over here to these two shapes, just to try to remind you what the role is that both the mean and the standard deviation play on your distribution. Remember, the mean affects position. So if I had two graphs that had the exact same standard deviation, where that describes the spread of the data, well then notice their curves look the same. It's like if I lined them up, you couldn't tell the difference. So they have the same distribution, and that doesn't have, just because they have the same standard deviation doesn't mean they have to have the same distribution. But in this case, we're saying bell-shaped curve, but the change here, the difference is a mu of 0 versus a mu of 3. So notice here, this curve's mu of 0, mean of 0, centers it at 0. And then if I go 1, 2, 3 jumps to the right, 3 standard deviations, because in this case it's a jump of 1, 3 standard deviations to the right, you basically get to where that graph has come down to the x-axis. Again, technically not stopping, we just stop drawing it. Over here, with the mean of 3, centered at 3, if I go 1, 2, 3 jumps to the left, that's where it's starting to trail off. And we can assume that's what's happening on these two. It's just not marked on the axis there. Now, with standard deviation affecting the spread, here we've got two distributions with the same mean. So that means they have the same center, right? Both these curves are centered right at 0. The standard deviation is telling you where you should expect this distribution to spread out to. With a standard deviation of 1, we should only expect to see it to about plus or minus the 3 again, right? 3 jumps of 1. Standard deviation of 2 means you should jump out 3 jumps of 2, so plus or minus 6, before you really start getting to where that graph is completely trailing off of our picture here. And so notice one thing that's important here, not only does the size or the distance left to right change, but if we were assuming these two graphs had the same number of data values, right? I don't know what these are, I don't have an example for them, but assuming they had the same data set, so say 100 values, right? Well, then it makes sense that if this data set, the second one, is more spread out, then it should be, if you want to call it lower, right, than this one. Here you're cramming all those data values between plus and minus 3. So you're going to have a lot more of them here than you will in that same range if you're spread out. We're saying the area of this figure is the same as the area of this figure, right? If you spread it out, it's like you're flattening it. You got to spread it out over more area, so it can't be as tall if you were talking about the same area underneath both those curves. All right, so going back to this idea of area under the curve representing probability, just a set of data here. We're looking at the height of a sample of 50 different 2-year-old males, 2-year-old boys. And so notice it is a bell-shaped curve, but we're using a histogram because we have discrete data here, so we can throw it into the different ranges of values. And so with this different set of classes, right, these are all the lower boundaries, I've shaded this one specifically. And so the idea is if we wanted to talk about the probability that a randomly selected individual, or 2-year-old male here, right, has a height between 34.5 and 35.5 inches, right? That's what this bar would essentially represent. The area is the probability. So now we've gone away from the uniform distribution where it was just that single rectangle, but it's still the idea of what this area represents. Now, in fact, it actually represents two things. And so down here, we've got what I'll call the two translations, the two interpretations of area under the curve. So with a random variable that's normally distributed, the area under the curve for any interval of values represents either, meaning You can pick either one. This is the one I've been focusing on, the probability that a randomly selected individual will have that characteristic. This is just more direct. This is the proportion of the population with that characteristic described. So in this case, the area here is nothing more than the probability, but that's also the proportion. If you looked at this data set and you looked at how many 2-year-old males have a height in this range, out of the total, it would be that, looks like 0.2, 20%, 0.20. So that area that we're going to be finding, and we're going to find it via other means involving our graphing calculator here very shortly, but that area has an interpretation of either the proportion that fall in that interval, or more often than not, we use it as the probability that a randomly selected person will have a characteristic value in that given interval. So they mean the same thing, they just are worded a little differently. And so, to see an example of that, we'll take a look at this 7.1.2. So we're told we have the weights of giraffes, and they are normally distributed. That's always important to have in this case. Mean of 2,200 pounds, standard deviation of 200, okay? So it says draw the normal curve with parameters labeled, okay? Here, not much more than working on drawing bell-shaped curves. Something close to that. You don't need to be an artist about it, but try to draw something with the bit of the curvature and the understanding of it having that kind of horizontal axis. So it says with parameters labeled, the main thing to me is that you know that the mean of 2200 labels the center of that graph. As far as the standard deviation being 200, right now I'm just going to write that off to the side. That doesn't do much for me, other than it does explain to me the idea of those jumps, and if anything, it could tell me what the plus or minus 3 jumps where those should be, right? So 200, 200, and 200 is 600, so I do know that around there somewhere, I should have 3 jumps of 200 getting me to 2,800, or 3 jumps of 200 getting me 600 below, so maybe around where that's starting to tail off, especially 1,600, you can use that information to kind of get that understanding of your picture you're drawing there. Now B says shade the area under the normal curve to the left of 2,100. Okay, so this is where we start kind of talking about a specific interval. We want to look at left of 2,100. Well, if 2,200 is here, 2,100 is somewhere to its left. Again, can't really be super accurate without a scale. So I'll just say there is the 2,100 on our axis, and we'll shade in the area to its left, right? Everything under the curve to the left of 2,100. And now it tells us, suppose that the area under the normal curve left of 2,100, so suppose this shaded area right here was 0.3085, okay? Now that makes sense. That's a value between 0 and 1 because the whole area is 1. It even makes sense because notice, since we're shading something left of the center, right, we would know that this shaded region couldn't even be half, right? It couldn't even be 50% because it's not past the halfway point. So it makes sense that that's 30.85%, so roughly 30% of our graph is shaded there. So it says provide the 2 interpretations. So we're saying that that area is 0.3085. And before I even get to the sentences I'm going to write and the interpretation, I just want to mention what I'm doing here and how I'm labeling it, because it's useful going forward. If you label all what we'll call data values down here that label your actual axis and write any areas, probabilities, or proportions above here, and I usually even draw it with these little arrows or lines drawing to the shaded region, that distinction and that organization can really help you understand where numbers go, what they describe, and what they do. So I really recommend doing that, as you're going to see me do throughout the notes here. But to the sentences, we're just saying, how would you interpret that number? Well, there's the 2 interpretations, the probability and the proportion. So let's go with the proportion one first. That was the first one listed on the other page of the notes. So nothing more than saying something like the proportion of giraffes with a weight, because that's what these numbers represent. And if our area was everything shaded left of 2,100, then we're saying a weight of less than 2,100 pounds, right? So the proportion of giraffes with a weight of less than 2,100 pounds is 0.3085. That information is telling us that that's the proportion of the population that has a weight that fits in that interval. So there's our proportion interpretation. Now for the probability, we just kind of rephrase it and we say the probability that a randomly selected giraffe has a weight less than 2,100 pounds is 0.3085. So again, the understanding of what that number represents, these two statements say the same thing. They just say it in different ways. Here you're more directly describing, in a sense, the population by describing what proportion of them fit a characteristic. Here you're using that same decimal as an interpretation of what's the chance, what's the probability that a individual out of that population fits this specific characteristic.